Hello class and welcome to Module 7. This week we're going to be applying what we've learned about the central limit theorem to statistical inference. We're finally going to be able to say something about the population with some level of confidence. All right, confidence intervals. When I began the course, I may have mentioned that the kinds of things we do in statistics can be roughly divided into two parts. There's descriptive statistics and inferential statistics. And descriptive statistics are where we are using statistics to say something about our sample. Inferential statistics are where we take sample data and we're trying to say something about the population it came from. And there's, roughly speaking, two types of things we can say about the population. All right, there's estimation, where we're trying to estimate some population characteristic. For example, the population parameter, like the mean or the proportion in a population. And then there is decision making. We're deciding between two contradictory hypotheses about the population. Is this true or is that true? Is the population mean 50 or is the population mean greater than 50? These are the kinds of things that we look at with decision making. And we're going to be looking at these two tasks this week and next week respectively. Estimation. And estimation, we really kind of have two kinds of estimates that we're interested in. The first is a point estimate. All right, so let's take a step back. I present you with a population and I say to you, okay, get a sample, and all right, you've got your sample, great. Now, I want you to estimate for me, what does the population mean? If you give me a point estimate, that means you're giving me a single number. All right? And the point estimate is pretty easy to calculate. We already know how to give point estimates, but the point estimate is virtually always wrong, which is to say, what's the chances that you get a sample from a population and you calculate precisely the population mean from your sample? That's not going to happen in virtually all cases. I guess it's technically possible, but that is not really going to happen in practice. Okay, so that's why the point estimate is always wrong. But okay, but maybe it's close, right? Maybe it's close to the population mean. That doesn't mean it's bad. Well, how close is it? That's what an interval estimate is all about. Rather than giving a single value, we're giving a range of values. It's a little bit more complicated to calculate, but not that bad. And so it's going to have some set probability of being correct. And how correct do you want it? What's the chance that you want it to be correct? Like, you can set that. So if I want to be really, really sure that my interval gets it right, I just raise that probability. That's called my confidence level. And I would just raise it really high. I'd say, okay, 99% or 99.9% or something like that. So to start out with, we want to look at point estimates. If you wanted to estimate the population mean, what do you do? What's the best thing to do? You can use any statistic to do it, really. Some might be better than others, though. The sample mean, the median, the mode, or maybe just bark out the number 42. Anytime someone asks to estimate the mean, you just say 42. Which is best? Well, maybe the mean, maybe the median. I don't think 42 is going to be very good. Each of these is going to have some variance to it, and it's going to either be biased or unbiased. Well, what does biased mean? The bias means, on average, is it correct on average, or is it not? Or is it too high on average? So turns out that the mean is an unbiased estimator of the population mean. That's unbiased. So on average, it's going to be right on, which is to say, if you have a population and you look at every single possible sample mean that you could get, all of the different samples you could take, the average of all those sample means is going to be the population mean precisely. So it's unbiased. It's an unbiased estimate. But there might be other unbiased estimators, right? So how do you know that the sample mean is better than those? Well, we have this second kind of determining factor of what makes an estimator good, which is least variance. Of all the unbiased estimators, this one has the smallest variance, which is to say, if you do a sample and get a sample mean, get another sample, do a sample mean, and do it again and again, they're going to vary from each other a little bit by a little bit. Well, the sample means are going to vary less than any other unbiased estimator that you could cook up. The number 42 has zero variance, right? If no matter what population, I just say the sample mean is 40, or I just say the population mean is 42 every single time, well, that has zero variance. Well, that's all fine and dandy, but it's super biased. 42 is going to be, depending on the population, it's going to be very biased to, like, it's biased negatively or positively, right? So that's not the best estimator. It's very biased, even though it has zero variance. So anyway, suffice it to say now that the sample mean is the best point estimate for the population mean. It is the best because it's unbiased, and of all the unbiased estimators, it has been proved, and some brainy people have done this. They have proved you can't make an estimator that is better, that has less variance. All right. Now, the central limit theorem, if you recall, it says that that the sample mean is going to be approximately normal. It's going to follow a near normal distribution, and we have a formula that tells us what its mean is going to be and what its standard deviation is going to be. Oftentimes, books will say, if you know the population standard deviation and the sample size is at least 30, you can use a normal distribution when modeling the sample mean. But you should use a t-distribution otherwise. And the t-distribution is just another continuous distribution. It has a little bit more probability out in the tails. It's maybe a little bit more of a cautious distribution. It gives a little bit more likelihood to extreme values than a normal distribution. But think about what we're saying. The book says, if you know the population standard deviation, well, that's just silly. How would we even know the population standard deviation? We never know the population standard deviation. We would only know the sample standard deviation. How would you know the population standard deviation and you don't know the population mean, right? So just use the t-distribution all the time when you're doing this inference, when you're using the central limit theorem for confidence intervals. And in a moment, I'll tell you how we do it for confidence intervals. What is the t-distribution? Student's t-distribution. Student was this guy. He took the name student as a way of kind of being anonymous. When he published this paper about this distribution, there's some history there I'm not going to get into because I actually don't know all the facts. But anyway, it's a continuous distribution. It has one parameter which is called degrees of freedom. The mean of the t-distribution is 0. The degrees of freedom, in our case, for the purpose of confidence intervals of the sample mean, confidence intervals for the population mean, the degrees of freedom is just 1 less than the sample size, n minus 1. And what I'm showing you in this picture is as the degrees of freedom gets bigger and bigger and bigger, the t-distribution curve more and more and more approaches the standard normal distribution. You can see that with 1 degree of freedom, the peak in the middle is rather low and the tails are rather high. And as the degrees of freedom increases, the peak raises and the tails shrink until finally you get to the standard normal curve. So when you're doing confidence intervals, use a t-distribution. If you have a small sample size, it's the right thing to do. If you have a large sample size, it approaches the normal distribution anyway, so just use the t-distribution. All right. What is a confidence interval? Finally, I've been saying this whole time. What is a confidence interval? Well, here it is. It's a point estimate plus or minus a margin of error. That's what it is. So I'm going to have a lower bound and an upper bound. That's my interval, and I give a certain amount of confidence that my interval is correct, that it really does get or capture the population mean, or the population parameter I'm trying to estimate. For the population mean, the margin of error is found by finding a critical t-value and then multiplying it by the standard error of the mean. We've looked at the standard error of the mean formula before. The critical t-value is found from a t-distribution. It's just what value gets the confidence amount kind of in the middle. So, which is to say, if I'm looking for a 95% confidence interval, I want to find what's that t-value that keeps 95% of the probability in the middle, and then the remaining 5% out in the tails. Okay, that's it. That's the idea for a confidence interval. I'm going to be doing some examples of confidence intervals in the next video using stat powers, but for this purpose, that's kind of enough to understand. Now, here's another principle that you should keep in mind. As you get a bigger and bigger sample size, that's better, of course. And why? Because the margin of error is going to be getting smaller and smaller and smaller. Because, recall, the margin of error is this critical t-value, which is independent of the sample size. Well, it's related to the sample size only through the degrees of freedom, but that's not going to have a big impact. But the standard error is, remember, you're dividing by the square root of n, the square root of the sample size. So as the sample size gets bigger, that standard error is going to shrink. Therefore, the margin of error is going to get smaller. My confidence interval is going to get smaller. But if I increase my confidence level, the margin of error will get bigger and bigger because my critical t-value is going to go out further and further out. Show you again, if rather than 95% confidence interval, I want 99% confidence interval, to capture 99% of the probability in the middle, I'm going to have to get those tails smaller. So the little lines are going to go further and further out, right? Well, that is going to translate into a wider confidence interval. Okay. Straightforward, should make sense. The other kind of confidence interval that we often do in an intro stats course is looking at population proportion. The population proportion because the population proportion is, it's related to a sample sum, the central limit theorem applies to that as well. So roughly speaking, the central limit theorem says that the sample proportion, the random variable, which can be like a sample proportion is like an observation from this random variable. Okay. Approximately follows a normal distribution, with the mean of this distribution equal to the population proportion, and the standard deviation of the population proportion, or of the sample proportion, sorry, is this formula: square root of p times 1 minus p over n. Now, there's some things that you need to bear in mind. If my sample mean or sample proportion is really close to 0 or really close to 1, this can fall apart. And if I have a really low or really high sample proportion, this is only good if my sample size is really, really big. Truthfully, A binomial distribution is a much better way of modeling this sampling distribution of a sample proportion. It is not so easy to do, and that's why it's often not taught in an intro stats course, but you can use technology to do it very easily. So I think that we should be transitioning over to using the binomial distribution for a more precise confidence interval calculation. But at any rate, if you're trying to estimate the population proportion, what should you use? Use the sample proportion. Why? But it is wrong. Why is that wrong? Well, because the point estimates are virtually always wrong, technically wrong. You're not going to be precisely estimating the population proportion, but it might be the best point estimate that you can get. Now, a confidence interval can be made for a population proportion. All right, again, we've got the confidence interval is going to be the point estimate plus or minus a margin of error. If you're doing an approximate confidence interval, you should use the normal distribution, not a t-distribution for the proportion. People don't ever use t-distributions in this situation, but a binomial is a much better way of doing it, to be exact, to be more precise. Anyway, the principle is pretty much the same, though. It's the point estimate plus or minus a margin of error. So if you're going to do it using the approximation, using a normal approximation, you find z values which are going to trap, from a standard normal distribution, which traps the amount of confidence in the middle, and then you're done. Of course, I'm going to show you how to do this using technology in the next video. And here's kind of an example of understanding how to interpret confidence intervals. So let's say you make a confidence interval for the population proportion. Say, okay, I'm gonna estimate with 95% confidence that p is between 0.24 and 0.36. So let's say that was my conclusion. I could say in words, we are 95% confident that the interval from 0.24 to 0.36 surrounds or captures p, the population proportion. I'm 95% confident in this interval. And a way of understanding what that means, if we were to sample again and again and again and again and again from this population, and every time we sampled, we calculated a confidence interval, our interval should be correct and correctly capture the population proportion roughly 95% of the time. Or in other words, it's going to miss the mark about 5% of the time. And this illustration shows what would happen if you have a population proportion of 0.3, and I think I did 100 different samples and confidence intervals from this population. And actually, if you count it up, there are 7 times that it misses the mark. 7 out of 100. And that's within reason. That's what we would expect to see. Anyway, that is the idea for confidence intervals. And I'm going to show you how in practice we're going to calculate confidence intervals in the next video.